Welcome back, Focus Learners. Okay, I am absolutely thrilled to have you here for today's explainer because we're looking at something truly extraordinary. We are going to decode the fascinating step-by-step molecular factory operating quietly inside plants, the dark reaction of photosynthesis. If you've ever wondered exactly how a plant builds its own food out of seemingly thin air, you are in the exact right place. We're going to map out the exact cellular math and the machinery that makes the whole shebang happen.
To make sure we grasp everything perfectly, here's our technical roadmap for today. We'll start with the light connection, check our essential chemical inputs, and then dive right into our three key stages: carbon fixation, glucose production, and RUBP regeneration.
Okay, let's dive into this with Section 1, the light connection.
First things first, we gotta clearly distinguish this from the light reaction. That one happens over in the grana, and its entire job is to create an energy power grid, specifically ATP and NADPH. But our focus today, the dark reaction, that takes place in the stroma. And hey, quick side note, despite the name, the dark reaction doesn't only happen at night. It's just called that because it doesn't need direct light. Instead, it acts as a molecular factory right there in the stroma that relies entirely on that ATP and NADPH power grid we just mentioned. Without that energy, the factory completely shuts down.
Moving right along to Section 2, Essential Chemical Inputs.
Before we start up the assembly line, let's do a quick inventory check. We need carbon dioxide, or CO2, which flows in from the atmosphere through tiny pores called stomata. But while the CO2 is an external delivery, the rest of these ingredients, RuBP, Rubisco, and those ATP and NDPH energy sources, they're already waiting on the factory floor in the stroma. Let's unpack those unfamiliar terms real quick, starting with RuBP.
So, RUBP, ribulose 1,5-bisphosphate. I know, heavy jargon, right? But conceptually, it's actually super simple. Picture it as a waiting 5-carbon molecule, whose literal only job is to act as a catcher's mitt for that incoming atmospheric carbon dioxide. That's it.
And right next to it on the floor, we have Rubisco. Now, it kind of sounds like a brand of crackers, I know, but think of it as the essential chemical worker on our assembly line. You see, CO2 and RuBP, they won't just hold hands on their own. They need a catalyst. Rubisco is the hard-working enzyme that forcefully binds the atmospheric carbon dioxide and our 5-carbon RuBP together.
Which brings us to Section 3. Stage 1, carbon fixation.
We're officially entering Stage 1, carbon fixation. But just to anchor ourselves, keep in mind that we are looking at a continuous 3-part cycle here, where every single step feeds directly into the next. Let's look at the exact chemical math of this fixation step. Our hard-working enzyme, Rubisco, grabs that 1-carbon CO2 molecule and literally smashes it into our 5-carbon RUBP catcher's mitt. Simple math, right? 1 + 5 = 6. But here's the catch. This newly formed 6-carbon compound is highly unstable. Like, it cannot stay in this form for long.
And that takes us to Section 4, Stage 2, glucose production.
This is the exact moment our power grid kicks in. The energy from the light reaction, those ATP and NADPH molecules, is finally spent here. The factory uses this energy to break down and rearrange that highly unstable 6-carbon compound. The goal? To forge a stable, life-giving molecule of glucose. But to make this work sustainably, the factory requires a very specific batch size.
Now, what's really interesting is the mathematical secret of this whole cellular factory. It comes down to a single number, 6. To successfully output one complete glucose molecule and keep the cycle alive, the plant needs exactly 6 molecules of CO2 and 6 molecules of RUBP entering the process simultaneously.
Let's slow down just a second and walk through this precise carbon math step by step, because it beautifully illustrates the efficiency of nature. If we input 6 CO2 molecules, well, that's 6 carbons. If we input 6 RUBP molecules, remember, those have 5 carbons each. That's 30 carbons. Add them up, and we've got a total pool of 36 working carbons on our factory floor. But check out our output. One single molecule of glucose only requires 6 carbons to build.
So out of our massive pool of 36 carbons, we only use 6 for the plant's food. 36 minus 6 leaves 30. So what happens to the remaining 30 carbons? I mean, they don't just vanish into thin air, right?
That mystery brings us perfectly to Section 5, Stage 3, RUBP regeneration.
Here is the factory's vital reset mechanism. Those 30 leftover carbons are perfectly recycled. Think about it.
If you divide 30 carbons by 5, you get exactly 6. The plant is literally using those leftover carbons to recreate the exact 6 5-carbon RUBP molecules we started with. The catcher's mitts are completely rebuilt, which allows the entire cycle to just start all over again without skipping a beat.
Think about the magnitude of this for a second. This isn't just a neat piece of cellular trivia. Without this continuous regeneration step, the dark reaction would instantly shut down after making just one molecule of glucose. The factory would run out of catcher's mitts immediately. It's this beautiful, continuous loop of regeneration that makes sustained plant life possible.
And that brings us to our final thought today. So, how does this invisible, microscopic, continuous loop of chemical math sustain almost all life on our planet? Well, every leaf you see, every piece of food you eat, relies entirely on this exact process. Without this perfect carbon accounting happening quietly in the stroma, the base of our planet's food chain simply collapses. Pretty mind-blowing, right? So as you go about your day, I leave you with this to ponder. How incredible is it that the macro survival of the Earth is entirely dictated by the flawless math of an invisible molecular factory? Thanks for exploring this explainer with me today, and keep your curiosity focused.